Welcome back. We're going to move on today. I want to move on to light, a new topic, and specifically this week, I'd like to start by talking about reflection of light. Um, Now, before we start, I'd just like to say that normally this is a topic where it'd be very heavy on experimentation in the lab, and normally I'd teach it with you doing these experiments as we go along. That's not going to be possible at the moment, so I know it might be difficult for you to catch everything I'm going to try to explain. I hope I do a reasonable job. It's going to be much easier when we get back to the lab and you can actually do this by experimentation and you can see it yourself. But please just bear with me. Do your best to try and follow everything that I say. I'll do my best to make it clear, and if it's not, you've got to come back to me with your comments and questions, please. Okay, so before we start, I just want to talk a bit about the way that we draw light diagrams, specifically reflection. If you can see this diagram above my head, this part here, that's the symbol for a mirror. It's a straight line. Well, it's the symbol for a plane mirror. We're only going to look at plane flat mirrors. We're not going to look at curved mirrors in this section. So a plane mirror, flat mirror, is a straight line with these dashed lines underneath it. The dashed lines are actually called silvering. And that's because hundreds of years ago, mirrors were really expensive items. They were actually made by having a layer of glass, and underneath there would be an actual layer of silver. So if you want to draw a mirror, you put the silvering underneath the glass layer. Okay, here we've got a ray of light hitting the mirror. That's called the incident ray. Incident means hitting. So this is the one that's coming in to hit the mirror. And here obviously we've got the reflected ray, which is the ray of light that's heading away from the mirror. Okay, and there's two angles we need to know about. There's this angle and this angle. The angle is always measured away from something called the normal line. The normal line is a line, a dotted line that we draw that is perpendicular or 90 degrees from the surface that the incident ray is hitting. We always measure away from the normal line. This angle from the normal line to the incident ray is called the angle of incidence. And obviously this angle away from the normal line to the reflected ray is called the angle of reflection. I hope that made sense. Okay. Here is the same diagram, but slightly larger with a bit of added text. The reason why I've put this above my head, it's the one thing I really want you to take away from this lesson. It's called the law of reflection. And the law of reflection says that the angle of incidence equals the angle of reflection. So let me just draw a couple of things on here. All right, the first thing I want you to realize is that when we're looking at a ray of light, remember you're already used to seeing a wave or a transverse, it's a terrible wave. A transverse wave looks like that. If you're looking at it sideways, you've got a peak and a crest. The ray is what you would see if you're looking down on top of the transverse wave, and you know that light is a transverse wave. So what you could actually see here is crest to crest to crest to crest. Obviously those should be the same size, and it's the same coming off as well on the reflected ray. So we're looking down on a ray, and we're basically looking at wavefront to wavefront. Okay, this is the incident ray. It's hitting the mirror. We've drawn in the normal line, which is at 90 degrees to the mirror itself, and we can, as we saw before, draw two angles. The first angle we'll draw is away from normal to the incident ray. That's called the angle of incidence. When I was at school, actually, we were always taught to draw the angle of incidence as a small letter I with a little hat on top to show that it's an angle. That's the angle of incidence. And here we've got the angle of reflection. Again, we measure away from the normal line, and you can show it as a small r or a small r with a little hat on the top. And all that this law of reflection tells you is that when you've got a ray of light hitting a mirror and reflecting off, this angle will be the same as that angle if you measure it with a protractor. Okay. Hope that made sense. That's the law of reflection. Okay, moving on again. One use of this law of reflection could be in a periscope, the kind of periscope you see on a submarine. This submarine you see here, it's got 4 periscopes, obviously one for each beetle. Yeah? But the way that a periscope works is a simple periscope actually. You can make it with mirrors, you can also make it with prisms. A very simple periscope is 2 mirrors, 45 degrees. This ray of light is incident to this mirror, and if you took a protractor and you drew a normal line at 90 degrees from the mirror, I'll do it as a dotted line, it would look like that. This angle would be your angle of incidence, would be equal to that angle, which would be your angle of reflection. It goes vertically downwards, hits the second mirror. We can put in another normal line at 45 degrees to the mirror. Now this angle is your new angle of incidence, and it would be equal to that angle of reflection. The ray of light would come out horizontally and it would hit your eye. So you would see, your eye would see an object that is actually up there. You'll be able to see the object above the water or above a wall. So that's one use of the law of reflection. Okay. Were you with me so far? The next thing on the syllabus is that we need to think about how images appear in mirrors using the law of reflection. Obviously this guy is seeing himself slightly different to what he really is. But when you actually look in a mirror, what you see is an image that is the same way up as the object. You don't appear upside down when you look at yourself in a mirror. You see an object that is the same size. You see an image that's the same size as the object. And you see the image of yourself basically the same, it appears to be the same distance behind the mirror as you are in front of the mirror. And the last two, that might take a bit of explaining. The image is laterally inverted. Now you know this. It appears that your left-hand side appears on the right-hand side of your image in the mirror, and vice versa. It seems that your right-hand side of your face is your left-hand side in the mirror. It's laterally inverted, not upside down, but sideways inverted. And finally, we'll see this quite a lot as we go through the subject of light. The image that you see in a mirror is virtual. That means it's not the same kind of an image that you see on the projector screen in the classroom. The image on a projector screen is real. You can focus the rays of light onto a screen, and therefore we call it a real image. The virtual image you see in the mirror, you can't put that onto a screen. It basically exists in one place, and that place is in your brain. It can't be put on a screen, it exists in your brain. Now, I hope that made sense. Now take a look at this guy looking at this object on the floor, a football. Here is the object, this football, and here is the image that the guy is seeing in the mirror. This blue line represents the mirror. I should really put silvering on, very quickly, on this side of the mirror to show which side is the object and which side is the image. Okay, so this guy, the football, is giving off light. There's two types of objects that you can see. Objects that give off their own light, or in this case, the football is not giving off its own light. It's giving off light that's reflected from the sun, or from the light in this guy's bathroom. We don't need to show all the rays of light that are leaving the football. They're going off in all directions, but we can look at 2 rays of light that are leaving the football, these 2 green lines. These 2 green rays of light are incident on the mirror, and they're reflecting off the mirror. We can put a normal line here, and a normal line there. And you can see that the angle of incidence here is the same as the angle of reflection, hits his eye. And here the angle of incidence is the same as the angle of reflection, and that ray of light hits his eye. We'll look at this in more detail in a second. But what his brain is doing, presumably he's got a brain up here somewhere, his brain is taking information from his eye, and his brain, or your brain, is calculating where he, I think it's a he anyway, where he thinks those rays of light are coming from. He thinks those rays of light are coming from this point behind the mirror and this point behind the mirror. And what his brain is doing is constructing an image of where he thinks that football actually is. That football is the same distance behind the mirror as the object is in front. It's upright. He doesn't see the bottom of the football as the top, or vice versa. It's the same way up. Same distance behind as in front. Laterally inverted, and as we said before, he sees a virtual image of that football. He can't put the image of the football onto a screen. It's a virtual image. Right, okay, I hope you're keeping up with me so far. So we've covered the law of reflection. Let me show you the same idea as the football in front and behind the mirror with a slightly better diagram. All right, so it's very usual in light diagrams to show an object as an arrow. I've shown it as a red arrow here. The reason why an arrow is useful is that an arrow has a bottom and a top. We'll say the top of the object is where the arrowhead is. Now, here's your eyeball, and here is a mirror. Again, we should show the mirror with silver ink, to show which is the front of the mirror and which is the back of the mirror. So your eyeball, here's your eye, is going to create an image of the object behind the mirror. The question is, how does it do that, and where is the object? Where is the image going to be of this object? Okay, so the object, it's giving off light in all directions, and it's doing that because light is hitting it from the sun and reflecting off the object. In order to find out exactly where the image is, we need basically two rays of light that we're going to follow. Let's start by following this ray of light you can see here. Okay. So we're going to follow this ray of light. This ray of light is leaving the top of the object, this one point here, and it's going to hit the mirror. Let's follow it through to the mirror. It hits the mirror, it's an incident ray. We draw the normal line, and then we show the ray of light reflecting from the mirror. Now, just as before, let me draw in this, measured away from normal is going to be the angle of incidence, and this is going to be your angle of reflection. And the law of reflection tells us that this angle, if you measured it with a protractor, is exactly the same as that angle. It looks about the same. Okay. Let's follow that ray of light backwards down to the mirror, just like we did with football. And the eye sees the top of the object at this point. Now again, just as we said with every image in a mirror, it's laterally inverted. It's the same distance, if we measure it with a ruler, behind the mirror as the object is in front of the mirror. It's virtual. It doesn't exist on a screen. It's only going to exist in the brain of you or this person that's actually collecting the light with the eyeball. We can do the same thing with a second ray of light. We'll draw a second ray of light, slightly different angle coming away from remember it's coming away from the object in all different directions. This one is hitting the mirror at a different normal line, different position on the mirror. The first one hits here, the second one hits here. It's going to reflect to the eye. Again, in this case, here is your incidence angle, or angle of incidence, and here's your angle of reflection. The law of reflection tells us they're exactly the same size, reflects off, hits your eye, and the brain again follows that ray of light backwards and calculates where it thinks it's coming from. And it's coming from exactly the same position again behind the mirror. We could do that same idea for every point on the object. And if we did that, we would reconstruct every point on the image the same distance behind the mirror as the object is in front. Okay. I hope that made sense. I found it very difficult to try and explain without the help of some apparatus. Obviously, I can try and get some better videos where you can actually see somebody doing this experiment in practice, and you can prove it for yourself. If you have mirrors in your house, which I'm sure you do, you could play around with images and objects and images, and we could even try some mirror writing, things like that. But I don't want to do too much in this video. The main thing, as I said, that I want you to come away with is what you can see above my head here in this box. It's the law of reflection, and the law of reflection tells you that the angle of incidence is always equal to the angle of reflection. Please take care that you realise that when you make these reflection diagrams, you've always got to put in a normal line, and the normal line is at 90 degrees to the mirror. Okay, please, when I set you some work with this, I'm very happy to take your comments and try and answer your comments, and we'll try and do some individual Google Meets to try and clear this up. Okay, take care everybody, and try the work that I'm going to set with this. Take care of yourselves and your family, and I'll speak to you during the week. Okay, bye-bye.